Hi everyone, welcome back. We continue on this and today we are gonna learn about the covariance matrices. The first is gonna be the process noise covariance, and the second is gonna be the measurement covariance matrix, and the last is gonna be the error covariance matrix. Actually, these two are very similar to each other about the purpose of the usage, and the last one is gonna be working for the initialization part of the motion. Maybe we can switch to the code part and understand more clearly why on the simulation example. Also, I need to repeat again, maybe who the people who are directly watching this video, we are not explaining all of the code at one time. We are going by one by. We already explained here, and we continue with the next lines. So now we are gonna focus on the covariance matrices. Actually, we are setting covariance matrices via on the set identity function. So maybe first of all, before assigning the parameter, we need to see what is the default value of this process noise covariance, and just try to see how it looks like from the console, and after setting how it looks like. Let's see. Okay, the first one is you see in here there is a binary matrix, so it's 4 by 4. Also it's up to your transition matrix. Since this is 4 by 4, this is gonna be defaultly 4 by 4, and if you since whatever scalar value you give into here is gonna change the diagonal values. So currently we are giving a value something like this, and it's assigning according to here. And yeah, so before assigning it looks like 1, and after assigning it's like this. So just to remember how it looks like, for example, our example was looking like this. So again, to understand the purpose of this process noise covariance, we need to check in the edges, in the changing direction part. For example, when the direction change of this white ball in here is still trying to continue on the previous direction. So this is about how we set this process noise covariance. For example, if we set this little high, which is 1 is really high, also maybe we can just comment out this because the default one is already binary matrix, which is taking the 1. Then we can compare again how it looks like. You see it's adapting itself in the edges very clearly, very faster. For example, here you see it's little going that direction, but faster is adapting itself. So for some maybe in some cases this is needed, but in some cases this is needed. So it's up to the case you are dealing with. In some cases you want the Kalman adaptate to the change of the direction faster, but in some cases you little wanna it continues on that direction. So this is changeable according to the cases, but I think you understood. If we set this value higher, it's gonna adaptate faster. But if you for example, our previous one was like this one. If you increase this, then it's gonna adaptate really lately. Maybe we are gonna see something interesting. Okay, it goes, yeah, you see it's really late coming behind of the true position. So it's really late because it's adaptating lately. So it's working in this direction. Also similarly, this measurement noise covariance, or if the people who are watching this video, if they know the clear difference between this about the usage of purpose, they can tell because they are working very similarly. And this can stay, let's say, like this. But for example, if I set this 100, and let's see how it looks like. Okay, yeah, now it's increasing the measurement noise covariance. It's not letting the adaptate faster, but if you make it, if you give it a low value, which is for example like this, then see how it looks like. You see it's adaptating very faster. So there is an opposite logic between measurement noise and the process noise. If you increase process noise, it's adaptating faster. If you decrease the measurement noise covariance, it's adaptating faster. But reality, the purpose, they are just about the adaptating the position faster or slower. So this is the purpose I see is like this. So if there are any other difference, the major difference between these two, you can comment, so I can check also, because I know as like this. Okay, maybe we can back to the first position. it was like this. So we can switch to the covariance matrix. The defaultly maybe we can give a small value which is like this and check how it looks like. Okay, since this is the about the beginning of the motion, for example, now my white ball in there and it's trying to catch the white ball, but you see giving lower value is at the beginning is not easy to find the correct point for the initialization. But if you give a high value, for example, let's say 1000, and okay, let's check again. Now I'm gonna press to my keyboard one time and two times, so it's directly finding the correct root position. So for initialization part, if you want the Kalman filter adaptating to the correct position faster, you need to give this error covariance matrix in a high scalar value. Accordingly, you can change position if you want. If you do not want it adapted faster at the beginning, so you can change again. And maybe we can also one more for checking how it looks like this covariance, and just copy here and just to see the default value. The default is 0 as you can see in here, and if you change this, the diagonal values are changing also. So all of them is also 4x4, is according to the input transition matrix you are giving. And yeah, for this video I just wanted to explain set identity function and how these covariance matrix are affecting our Kalman filter. And done for this video. See you in the next videos.